Ladies and gentlemen, welcome on our regular series of Connection Wednesdays for IDEA StatiCa connection. Today we will focus on backlink. I hope you can see my screen. Let me introduce today's presenters. Today will lead you through webinar Mr. Vít Hurčík.
Hello, ladies and gentlemen.
And myself, David Kučera. Hello. We both are product engineers. Just a quick recapitulation. If you want type in the questions, please do it. You can do it in the question panel, in the question tab, where you can input your questions anytime during the webinar. In the first part of our webinar, we will go through complex joint, which was provided by company Severstal. And you can see this is a really very nice joint with a lot of stiffeners. So many thanks to the company Severstal. And we will go through the backlink results. In the second part of our webinar, my colleague Vít Hurčík will show you Helpdesk highlight, and you will find out more about FinVolt members. Once again, many thanks for providing connection. Many thanks to company Severstal. This company is situated in Russia, St. Petersburg. It's design and consulting company, and they mainly deal with industry buildings. On the pictures you can see some of their projects, for instance, plant for the production of liquefied gas or Kingisepp ammonia. First of all, let me introduce a little bit of theory about backlink. Backlink analysis is only one kind of analysis we provide for you. This is this one. IDEA StatiCa connection is able to perform linear backlink analysis and provide the user the factor of the critical load and backlink shapes. This backlink analysis is geometrically linear. It doesn't take into account non-linear analysis with imperfections. This is really important for FinVolt members, where geometrically linear analysis isn't sufficient. And about FinVolt members will be the second part with my colleague Vít Hurčík. I'm sure that all of you know the limit value for backlink. It is for Eurocode, it is in accordance with Eurocode 1993-1-1, clause 5.2.1, and there is limit value 15. It means what's under the limit, what is under the limit 15, it's unsatisfactory. So it's nothing new for you as an engineers. I would like to clarify terms as global backlink and local backlink. What does it mean, global backlink? It is backlink of the whole members. On the picture below, we can see the plate. It is part of the member. It is elongation of the member. So it means we are talking about global backlink. In this case, backlink factor is definitely or couldn't be definitely under the limit 15. Then we have local buckling. It means we are talking about buckling of individual plates. It's visible on the pictures below, some stiffeners, some reinforcement, or web in the web of the column in the shear. Our university team, led by Professor Wald, made an experiment, and they found out that in this case, local buckling, it's possible to use the limit value 3. But please keep in mind, this is only based on our experiments. It's not covered in the code. So if you want to use this value 3, it depends on your engineering judgment. But we definitely recommend use limit 15. And now let's take a closer look at the first project. Company Severstal created this connection in Tekla structures. They took an advantage of beam links, and connection was exported to IDEA StatiCa. There it was loaded, and they found out that something is unsatisfactory. In few seconds, you will see what. And therefore, connection must be reinforced. And one of the options was to reinforce web of the column. Just now, we can skip directly to the software, to the IDEA StatiCa connection. I have calculated the connection for you in advance to speed up the webinar. In the in the right part of the 3D window, we can see a summary of the results. Almost all of the checks are satisfactory, except for buckling. We can investigate buckling a little bit more. To do that, let's go to the check and the tab buckling. We can display buckling shapes. Just now I want to display the first buckling shape. But of course you can display any other buckling shape which you desire. Let's go back to the first one. As was mentioned before, the limit is 15. We are under the limit and we have to do something with the connection. The connection was reinforced and we applied reinforcement on the web of the column. So let's do that and we will see what will happen. We go back to design and at operation stiffening plate. Let's adjust proper values for this plate. I can make it more visible for you. We switch to transparent mode. You can see that the plate was added. And now the best way is to select origin of the plate for the member 1, and it's located on the web 1. For this time, type of the plate is doubler. It's on the front size and I won't adjust welds. Let's use effective thickness of the weld 8 millimeters. And that's it. One plate was added. To speed up the process of modeling, let's copy the plate and use it on the opposite side. In the front, it's missing, and I can switch location of the plate from front to rear. And that's it. We have plates on both sides of the web. Let's add another stiffeners. To do that, let's use again stiffening plates. Let's adjust proper values for this plate. Just now, this is edit plate. The best way is to use origin on the plate, on this plate. So it's this one, and we want rib, location front, we set position and rotate the stiffener to the position. And the plate was added, and we switch both-sided fillet welds. Now I want place this plate between top flange of member 1 and this plate. The best way is to cut the plates by these two items. Let's select operation cut of the plate, and I want cut this plate by part of the member. It's top flange of member 1, and I want both-sided fillet welds. Let's copy the cut, the plate cut. Now I want to cut the same plate, but this time by plate, by this one. We change the surface of the plate, and that's it. The plate was added. Just now, let's modify a little bit shape of the plate. Let's go to the editor, and we want add chamfers for corner 1 and for corner 2 with value 50 millimeters. And that's it. Plate was chamfered. Just now, I will play with these 3 operations: stiffening plate and 2 cuts. I want to copy this plate to the opposite side and the same to the lower part of our connection. Let's copy these 3 operations. Just now, rotate it on the opposite side. So, the origin of the stiffening plate is this one. Location is rear. And that's it. I can move to plate cut. Now we won't cut this plate by top flange, and we can go on again this plate by this one and change the surface. Again, let's copy these 3 operations and set the plate to the lower part of the connection. Let's change position, and the origin of the plate is the same. We can change only cuts. So now this plate. So this is the same. Plate was connected, and the third operation, this plate will be cutted by this one, and that's it. And for the last time, copy these three operations and make the plate on the opposite side of the web. Origin plate is this one, location is front. Now we have this plate, weld was automatically done, and the opposite side we switch for this one and this plate, and again change the surface of cut, and that's it. We have final design of our connection and we can run the calculation. If you want to run backlink analysis, go to the check, and here is backlink. Again, I have calculated connection for you in advance, and just now we have the results. We can go to the backlink check, and you can see that it helped a lot. Now we aren't under the limit 15, and our connection is okay. So I am satisfied with this model. And if you want, you can investigate more results, or you can print directly the report. So we can go back to the presentation. And now we prepared for you a small poll. Just now it was displayed on your screen. So please think about it and answer it. And the question is, where the limit value alpha critical higher than 3 comes from? So what do you think? I can advise that this question was covered in the theory section. I can see that almost most of you voted, so let's give you 15 more seconds. It's quite easy question. So thank you. We can close the poll, and we will see what are your questions, what are your answers. Just now, let me give a word to my colleague with Určík, and he will explain Finvolt members.
Thank you very much, David, for the presentation, and I will take the word and I will continue with the second example. And we will talk about the Helpdesk highlight, thin-walled connection, and buckling issues. But the first thing, we have to mention a small amount of theory. For that, StatiCa connection is primarily dedicated to assessment of the connections of hot roll members which are not significantly affected by buckling, and the thickness of these members should be more than 4 millimeters. The geometrically linear and materially non-linear analysis is performed in our application, and that is the most important thing, geometrically linear. Thin-walled members actually must be assessed by geometrically non-linear analysis, because this analysis can take into account effective parameters of the thin-walled members. So if you still have to, or you want to use StatiCa connection to perform code checks for thin-walled connections, we prepared for you some hints. Please carefully evaluate each buckling shape. Do not rely on plasticity of the elements. Limit the von Mises stress to yield stress or even lower. And presented checks of the components are dedicated to standard members. As an engineers, you already know that checks for thin-walled members may vary and they have a different code. And the last thing, for the final decision, other tools has to be used to get a full picture. You can find this in our frequently asked questions in our resource center if you are interested to take a deep knowledge of that. So right now, let's jump right into the example to application, and we can go through that. We have designed this nice frame joint. We have here column with thin-walled C section. The thickness of this section is 4 millimeters. You can see it on the left side at the bottom. And the beam is with the same cross section, so 4 millimeters again. And the connecting plate, or the gusset plate, or we can say that it's a main plate of the connection, has only 3 millimeters of thickness, which is lower that we want to. And it's interesting that if you will calculate this connection, you will get all green Nikes, which make you maybe feel it's okay, but it's dangerous because buckling factor is only below 2. So let's go to the check, because I really need to evaluate carefully every buckling factor. And here in the tab buckling, I see all 6 smallest factors of the joint. So let's turn on the buckling shape, and immediately I can see that this is really dangerous because it is 1.6, and our really slender plate here in the connection has a tendency to buckle, which is not satisfactory at all. And what to do with that? For example, we can insert some stiffener, and we have several options, of course. For me, it will be the best or the most simple way to insert stiffener, and it can be welded, of course, if you want to. What is interesting, that with this welded stiffener, the buckling factor increases, of course, and if I will carefully evaluate it, I am over 2 now, and the plate doesn't have the tendency to buckle here anymore, and there are other places where is the connection slender. And because it's a it's a bolted joint, and this plate will be probably bended, I don't really want to have here welded plate, so I can add in a different way a stiffener, for example this one, uh, channel profile, and I can bolt it together, which gives me a better way how to build it, and I can evaluate again the buckling factors. You can see that here there's a tendency to buckle in this plate with thickness 3 millimeters, and again here in this plate. Yes, I can add a stiffener, but it's a never-ending process. So for me right now, the best way is to increase the thickness of the plate. So I prepare that in advance. And next step, so you can see that this whole plate now has the thickness 4 millimeters right here at the bottom, 4 millimeters, and the other plates too, because in reality it will be bended plate. And what about the results? Let's check it out. Let's go to buckling and buckling shape. Now it's even more interesting because we increase the buckling factor almost to 4. Now it's 3.55, 3.6, which is great. And there is another issue here at the bottom part of the plate. It has tendency to buckle, which we can prevent by adding some small bend here at the bottom. We can solve this factor. Next one, if we go through all of them, this is nice because the member has a tendency to buckle, and we can cover that by another check in another application or by a hand with effective parameters, of course. Next, another factor is the same in the member column. We can cover that. Next factor is here. So this this bended profile L shape has a tendency to buckle and open to the left. Maybe we can change that by adding some more bending, for example, like this, to this place, which will make it more stiffer. And that's a really nice engineering work to decide what to do with this. And we can go through each buckling factor like this, and we can make the connection safer. Another thing that I want to point out is that if we will go here to plates and check out our maximal equivalent plastic strain, we can figure it out that now we are less than 1%, which is great. We really don't want to have here, I don't know, 2-3% of the plastic strain because it can be dangerous. The members for class 4 and slender plates cannot be used for plasticity that much. So this is definitely good value. Maybe we can manage it to push it down a little bit to 0.5. That will be even better. And we talk about decreasing or limiting the von Mises stress or equivalent stress. Now here we have 440 megapascals, and I can show that these plates are made from high steel grade as 450. So it's a grade that we are not yielding. So that's great. And with this procedure, we can create the connection even more safer. So the message is evaluate carefully each buckling shape, limit the plastic strain, and even take care of the maximum equivalent stress. Don't rely on green Nikes and use your engineering judgment. So let's jump right into the presentation again. If you have still quite a time, so you can place your questions, and I will ask David. David, is there any interesting question from our customers?
Yes, hello. There was one question, or there were many questions, but we explained buckling, and there is one general and interesting from one of our customer. Do you recommend perform buckling check every time or only in some cases? Okay, thank you for this question. Each software can only help you. It is your tool, how to check something. Of course, here is the possibility of backlink check, and each check should be done for backlink. So in most of the cases, in most of the connections, backlink check can be the critical, especially when there is pressure force. So to be on the safe side, we recommend to you perform, of course, stress strain analysis and backlink check. And you know you are on the safe side and the backlink is checked. But the final decision about the backlink factor depends on you as an engineers, because you are responsible for your models and structures.
Thank you, David, for covering that question. And let's move forward. We will answer your question during the webinar right now. David is typing something, and I will cover the last things. As usual, after the webinar, will pop up for you a short survey. Please take your time and fill it, because you can tell us your opinion about this, and we are trying to do the webinars for you. So let us know what you think. A recording of this webinar will be available tomorrow, probably, at our webinars tab at homepage or at our YouTube channel. If you are not testing StatiCa already, you can get trial version for free at ideastatica.com homepage. There is a free trial button. And the most important thing of this, you can find all these informations in Resource Center, like the frequently asked questions that we explained and everything about the knowledge behind. The next webinar will be on April 17th, 2018. It will be about the new version StatiCa 10.0 for the steel and concrete. So if you are interested in the new features into a new version, just check in and attend on this webinar. Ladies and gentlemen, this is the end of our today's webinar. Thank you for attention.
Thank you very much for your attention, and we hope that the webinar was useful for you.
And see you soon.
See you.